specialist. My name is Kyu Young Han. Today I'm going to talk about our recent work 2.5D microscopy. We all love to use the wide field illumination or fluorescent microscopy because of many reasons. It provides high resolution, single molecule sensitivity, and also we can image a live cell. However, you may not be happy about the throughput. Typically, we can only image between 1 to 10 cells per second. If we compare this throughput with another technique such as flow cytometry, we can see the huge difference of the magnitude. So our group's one of the main motivation is to reduce the gap between the flow cytometry and this high-throughput microscopy using another imaging technique. If you take a look closely of how we can obtain a high-throughput fluorescent microscopy imaging, we can easily figure it out what is the main problem of this low throughput. We get the Z-stack, just simply image a different plane, and then we stitch the image in a different field of view. When you quickly add a typical number of the parameter, and then for imaging a single well of 96 well plate, it will take more than several hours. You can easily figure it out. The main problem is that very long serial Z-scanning. So to overcome this slow and low throughput in fluorescence imaging microscopy, people propose many different approaches to achieve fast volumetric imaging. One of the most popular approaches is simply scan fast, or we can just split up the multiple focal plane with a different area of the camera area. Or we can just simply use low numerical aperture objective lens to extend the imaging depth of field. However, all these approaches have a limitation of the low fluorescence detection efficiency. There is another way to achieve volumetric imaging, which is PSF engineering or point spread function engineering. Here we have a standard wide field microscope, and there's a relay imaging system. Instead of just using a normal detection PSF, we can engineer the PSF shape to elongate along the axial direction, like here. So we can add a variety of the module between this lens, for example, a difframometer or spatial light modulator, simply change the phase of the light. So in this way, without Z-scanning, we can capture all the 3D information as a single shot. Another interesting point is that most of the fluorescence community, if they are not quite interested in high-resolution 3D structural information, they just simply project all the 3D information to the single plane using maximum intensity projection to present the 3D object. Historically, we've been used a cubic phase for the tissue imaging. This is really great because we can extend the imaging depth from 0 to more than 20 micron or even 100 micron. However, as you see here, this cubic phase generate many side lobes on the XY plane. This is why it's very hard to reconstruct the XY information. So this is why we've been seeking to a new different PSF engineering technology to present to provide a minimal broadening of the lateral resolution, or to tune the depth easily, and also it could have high uniformity axial profile, also compatible with many organic fluorophore and other emitter. But finally, it has to be compatible with high NA objective lens. So this is our design principle of the new PSF engineering tool. So this is a normal PSF we intentionally apply spherical aberration in this PSF. As you see, the PSF is elongate along the optical axis. But this is not symmetric, so we binarize using the 0 and pi instead of continuous phase. Then we can have two different side lobe, the bottom and the top. But using the defocus term, we can move the side lobe close on the center. And then finally, we can have a very uniform, actually elongate, a symmetric PSF. We like to call this 2.5D phase filter. And then also we like to call our technique is 2.5D microscopy. Our approach has several good desirable property. For example, we can easily tune the imaging depth, simply changing these two parameters in the phase pattern. So this is a typical lateral and axial profile. As you see here, compared to low NA objective lens, 2.5D has much more flat axial profile. If you want to get more, even further flat axial profile, we can slightly dither axial PSF. So if we plot the lateral resolution versus axial resolution, we can clearly see what is the main benefit of our approach. For example, if you want to achieve 4 micron imaging depths compared to a clear aperture or low NA objective lens, the broadening of the lateral resolution is much less. So this is why we can obtain high resolution volumetric imaging. Once we simulate all the results, and then we want to confirm our idea using the experiment. We use the spatial line modulator as a phase module, and we just confirm the PSF. As you see that we were able to elongate the profile about 7 times, but the X profile only broader get 1.6 times. This is a single molecule imaging on the different imaging plane. As you expected, a 2.5D in different imaging depths, we can get almost same fluorescent intensity data. However, wide field microscopy, you can quickly lose the fluorescence intensity information. But I like to highlight our intensity at same illumination and same exposure time is actually 3 times lower compared to conventional wide field because our PSF get broader. So this is why if you want to have similar level of a signal to noise ratio of wide field, we need to use a 3 times longer exposure time. Next, we like to use our approach to single molecule fish. Our target system was EF2 in U2SN, and we use a 32 fish probe. And the left side is a 25 or 24 Z-stack using the wide field imaging, and it takes more than 10 seconds. On the right side, this is our single shot 2.5D imaging. It takes just 1 second. With this 3D Z-stack, we just simply maximum intensity projection. This is shown here. And we just compare side by side for the maximum intensity projection and 2.5D. On the right side, you can clearly see, depending on the threshold value, we were easily get the number of the messenger RNA. Messenger RNA. For example, the MIP number and 2.5D number was just only 5% difference. Also, each single molecule spot very well colocalized as well. However, you notice 2.5D imaging has slightly higher background because this is expected. It's higher than 1.7. But there's no big issue to select or identify the single molecule spot. It was very straightforward to extend the multicolor single molecule fish imaging. So we demonstrate size 3B label EF2 and Alexa Explore 647 labeled top to A. So in this case, we don't need to change the phase pattern because these two wavelengths, the imaging depth is deeper than the thickness of our cell V2S. But if we want to image full color, for example, DEPI, GFP, in that case, we might need to update different phase pattern to preserve the same imaging depths. This is a simple comparison of the imaging speed of the wide field versus 2.5D. So as shown here, this is a real-time result. As you see, a 2.5D complete 3x3 grid imaging. However, wide field imaging technique still imaging the first field of view. Of course, we can move forward to the high throughput 2.5D imaging. So we measure 2 by 2 millimeter square area, and we are able to analyze more than 2,000 cells, and then for example, we could analyze the nuclear size and also copy number from each cell. Then we showed a very good correlation value, which is also very correspond to the previous report. So I like to highlight the total imaging time for imaging this large area was just 9 minutes. Another benefit of our approach is that 2.5D use much lower light though, as shown here. See here, this is a different volumetric imaging time. As is shown here, the 2.5D photobleaching curve is much slowly decay. On the right side, we also image live cell labeled with SIR tubulin. So we were able to clearly see the cell's mitosis for very extended time. So we expect that much lower light dose of our technique can significantly reduce photo damage and photo bleaching. If our imaging depth is very large, for example, if the cells start to get divide, then initially the cell should be on the cover slip. But when it gets into the mitosis, the cell thickness gets thicker. So in that case, for conventional approach, we have to scan many steps. But in our case, just 4-step imaging, we were able to cover from 0 to 70 micron imaging depths for very long period. But this sample is a little abnormal because we can see the spot here. Okay. But as you expected, our technique is not quite impressive for the structural study because our lateral resolution is a little larger compared to maximum intensity projection, but still we can clearly observe microtubule structure with a single shot imaging. But of course, we can use the computation-based super resolution imaging techniques such as SURF, super resolution radial fluctuation. Simply find what is the maximum intensity pixel is heading to. So using that, we could get a higher resolution. But still, this is an ongoing project. In live cell imaging, we observe reflective mismatch aberration problem. With wide field, because of we used oil immersion and water immersion, a water medium. In that case, depending on the imaging depth, we've seen the PSF get quickly degrade. The main problem is the peak intensity is dropped significantly. But
This can be easily corrected by adding a phase, because we are using spatial light modulator. Then we could recover back. The same principle can be applied to our approach 2.5D. So as shown here, depending on imaging depth, we observe significant PSF change. However, if we add additional phase term, then we will basically correct the aberration. Our approach actually have a little problem in terms of detection efficiency, because we are using spatial light modulator. The SLM actually only respond to linear polarized light to the one direction, meaning that we have to discard 50% of fluorescent light using the this polarizing optics. So we are only collecting about 41% of the fluorescent light. However, we can easily achieve more than 90% of the detection efficiency simply designing a passive phase plate, as shown here. And then we can just use this as a kind of a filter wheel in our imaging system. This is really good. However, we cannot tune the imaging depth. Also, it's almost impossible to correct the aberration. Currently, we are conducting more experiment, which is a double pass configuration, meaning we are cycling the fluorescent emission light passing the fluorescent light to the SLM twice, and then we were able to get more than 75% detection efficiency. So this is a summary of our work. We developed a new high-throughput imaging technique 2.5D for faster high-throughput imaging. It provides high-resolution, single-shot volumetric imaging under epi-illumination wide field system. It's tunable, single-mode sensitivity, and multicolor imaging. Particularly, it's really powerful for single molecule fish imaging or other single molecule imaging as well. We expect our light dose could reduce photo bleaching and photo damage, and we hope it's going to be a very useful add-on to our other lifestyle imaging technology. So I'm one of the PI of the Dr. Andrew Belmont and Yaron Shavtar's the team. So we are studying nuclear speckle and trying to map the nuclear speckle component and to measure the dynamics. My part is developing lifestyle microscopy. I don't think we're not going to use 2.5D as a main technology, but there might be a niche application. For example, we can use 2.5D as a quick overview of the lifestyle imaging. For example, simply scan many different areas with low light dose. And whenever, if we find very interesting area, then we can switch to the conventional 3D G-stack imaging, then monitor a certain event. Also, we also are trying to develop user-friendly and affordable optical device for 4D community. Beside the 4DN, we are trying to push our throughput more than 100 cells per second without compromising the performance. And also, we are trying to improve the signal-to-noise ratio using the deep learning. And finally, this is the most difficult part. We need to more carefully measure the phototoxicity, because that actually very limited our lifestyle imaging for the 4DN project. So with that, I'd like to thank all my group members, especially this work is done by excellent student Kyu Young Han for herself. And also I'd like to thank all the funding agency. And thank you for your attention, and I'm happy to have your question.